This is week 5 of Applied Thermodynamics Problem solving session. So this week is about the internal combustion engines and air standard cycles will be coming in next week. So this is internal combustion engines. We will see 4-stroke, 2-stroke engines and their operation, and we'll see some numericals on those. So starting with we have engine can be any of two types. One is a power producing or can be a power absorbing. So that is classified into two. So if you see in case of power absorbing, there's an air compressor and refrigerators, heat pumps. So those are power absorbing. Normal refrigerator or a heat pump to heat like kind of an heater, and air compressor to compress air. You use it multiple ways. So those are power absorbing. But what we are looking at is power producing. So that if you see, power producing can be of three types. One is internal combustion, one is air motors, and other is external combustion. So what we are looking at this week is internal combustion, but that can be of external combustion. The combustion happening, if it's happening inside the engine, then it's an internal combustion. If it's happening somewhere else and you're using generating energy out of it and using that to produce it work, that's an external combustion. So that we'll be looking at in coming weeks. So again, those can be either of even though in an internal combustion or an external combustion, those can be of rotary type or a reciprocating type. So then if you're doing an internal combustion engine, because we will be looking at internal combustion engine this week, so it could be of reciprocating or rotary type. In rotary type, you have gas turbines or aircraft engines such. Those will be of internal combustion, and you have turbines inside. And other is the reciprocating type, which we'll be seeing this week. And the reciprocating type can be of two types. One is a spark ignition and is a compression ignition, or in general sense, if you want to have an idea, is a petrol engine and a diesel engine. So petrol engine uses a spark ignition phenomena, and a diesel engine uses a compression ignition phenomena. So the way the fuel and air mixture is ignited differentiates the two. One is a spark ignition and one is a compression ignition. Spark ignition can be then classified based on the fuel used and what type of the engine, how it is cooled. Is it an air cooled or in a water cooled? Air cooled is a normal which you see in a two-wheelers. You see an engine and you see there are fins out of it, small thin sheets kind of thing outside the engine. You can see that's a fins. So that is air cooled, and normally in cars and all you'll have water cooled. Other such bigger engines you'll have water cooled. And again, this both spark ignition and compression ignition can operate in a 4-stroke or a 2-stroke type. So we'll see that as well. So, and it can be classified in other ways as well, based on the valve and how the valve is positioned and how the engine cylinders are positioned. So they can be classified again. But the major classification is the internal engine can operate in a 4-stroke or a 2-stroke. Based on that, you can classify an engine, and in general sense, it can be a spark ignition or a compression ignition. Each can have operate in 4-stroke or 2-stroke, and what type of cooling is adopted in the engine. So these all are the major classifications you see in an engine. So we'll see. We have seen both internal combustion and external combustion. We classified. So we'll see what is an advantage of the internal combustion over external combustion, and what is the advantage of the external combustion over the internal combustion. See each of the advantages of that. So if you see reciprocating internal combustion engine have high overall efficiency. They have great mechanical simplicity. It's simple compared to the external combustion, and the weight to power ratio is generally low. So and 4 is, if the weight to power ratio is low, it's like for smaller weight you have more power. So that is weight to power ratio is generally low compared to an external combustion engines, and then it has generally lower initial cost because everything is happening inside, and you don't need a separate combustion chamber or something and take it, pump it or compress it and send it here. So that all is avoided. So the initial cost is very less, and it has easy starting from cold condition, and these units are compact and require less space. So these are the advantages of the internal combustion engines. But if you see what are the advantages of the external combustion engines, so if you see external combustion engine, the starting torque is very high, or generally high compared to the internal combustion engine. So because of combustion is happening externally, so you can use the fuels can be any kind of fuel. You can use a solid fuel, you can use a liquid fuel, or gaseous. Whatever fuel you can combust it and you can generate power. But in internal combustion, you cannot do it. You mix it with air, and the combustion happens inside. So there is a restriction on the type of fuel which you can use. So this even solids can be used advantageously in this kind of an external combustion engine. So due to external combustion, it is possible to have flexibility in arrangement. So how to arrange in the space, everything, so that you have a greater flexibility in case of external combustion engine. So these units are self-starting with working fluid, whereas in case of internal combustion engine, some additional equipments may be required to start the engine. So these are the advantages of the external combustion engine, and we have seen both the advantages of each of the combustion engines, externally and internal combustion. So now let's look at the engine, then how the engine looks, what are the parts of the engine. So I have shown a schematic of an air-cooled internal combustion engine. So this is just a general idea, but you can have a similar. Most of the parts which here will be similar. You see, the outer portion which is encompasses the engine is called the engine block. So that will be the engine block. Everything will fit in the engine block, and if you see the round circular portion at the bottom is the crankshaft which drives the piston, and it takes out the energy from the piston which is generating to a rotary motion with this arrangement of the crankshaft and the slider. So this is the crankshaft in which the piston is connected with the connecting rod. So this circular portion is the crankshaft, and then you have connecting rod, which is the rod with a small bigger rod connecting the piston here, and that is connected using a crank pin. And we have the bottom casing where the crankshaft is called a crankcase, and you will have lubricating oil and other stuffs there. And then the connecting rod is connected to the piston using the wrist pin or a gudgeon pin. In this, there will be a piston which will be moving inside the cylinder. It's called a cylinder in which the piston moves. There will be a piston ring connecting piston ring in between the piston and the cylinder. This is to stop the fluid expanding, the fluid which is there in the combustion chamber to not go out. So it will be like a seal. So that will act as a seal. So that is the piston ring which will come in between the piston and the cylinder. And then if you see a piston here, it's a flat top the piston, but the piston can have different shapes and contours at the top. It's called the piston crown, so it can have different shapes. And then you have valves here with the spring loaded shown. So there is exhaust valve shown in the right, and the inlet valve in the left, and the inlet port and exhaust port through where the fuel air mixture comes. And the outer portion we have shown some cooling fins, because this is air cooled. We have cooling fins shown here. So these are the major parts. I'll just show you an image of how the engine looks. You see, this is an schematic or a drawing view of an engine. So if you see the pistons, the multiple pistons are arranged in the crankshaft. It's connected to the crankshaft, and the crankshaft is connected to a flywheel. So the flywheel is required because even if you see in a 4-stroke, the power stroke happens only once in 2 cycles. So other cycles you don't have power. So this power is generated and kept in the flywheel. Excess power is generated and kept in the flywheel. So it provides a smooth operation and provides energy for retaining of the piston. So that is why the flywheel is used. And there's a motor connected, because for starting there is a starter motor there. And then at the top, if you see, there are 2 gears which are driven by the crankshaft. So these are the camshafts called. These are camshafts which have cams. So the cams are designed for for having the timings of the valve, when to open and when to close, at what rotation, what angle the valve should open. So those determines the cam profile, and the cams are designed such that when the pistons are expanding and you need an inlet air to come in, and then when after combustion, when the piston is compressing, the exhaust valve should open and it should go. So that to govern that, there's a camshaft which is driven by the crankshaft. It's placed at the top, that will open the valves, inlet and exhaust valves. So that's the one. And you have cylinders shown, and the crankcase and the crankshaft shown, and the other it'll have ports for water to enter for cooling, and any other I think that's it. And some engines may have a turbocharger or a supercharging provided. You see, these are the cams which are sitting over the inlet and exhaust valves. So these cams will, while rotating, they will push down on the cam, and that will open the valves. So that is one arrangement. So okay, going back. So see, we have seen the major parts involved in making of the engine, and we'll see the nomenclature. How we'll see how the engine for the calculation. What are the terms which is generally used? So the piston is shown, and the diameter of the cylinder is defined as bore, and then the length which the piston traces during compression or expansion during cycling, that is defined as stroke. And the volume in the cylinder at the top of the piston, which the minimum volume which is left out in the compression, or when the piston reaches the top during cycle, and the volume in the combustion chamber is called the clearance volume. And you have the inlet manifold for the valve, and exhaust manifold with the valve, and that is, the top is called the cylinder head. So the top where the piston reaches the topmost point, it's called the top dead center, and the bottommost point is called the bottom dead center. So the volume between the top dead center and bottom dead center is called as the displacement volume, or you can call it swept volume also, because the piston is sweeping that volume. So swept volume or displacement volume can be called. So that volume is defined by the bore and the stroke length, and the total volume of the cylinder minus the displacement volume will give you the clearance volume. So these are the general terminologies which is used in the engine. And one more important term is the compression ratio. So the compression ratio is defined as the total volume divided by the clearance volume. So it will come out to be 1 plus swept volume or displacement volume by clearance volume. So that is the compression ratio. and based on the bore and the bore diameter and the stroke length, the engine is defined as, if the stroke length and the bore diameter are equal, it's called as a square engine, and if the diameter is more than the stroke length, it's called a over square engine, and if the square if its bore is less than the stroke, it's called a under square engine. So if you see, in case of an under square engine, the diameter will be small, so the compression will take place faster, and but in case of compared to the one over square engine, and but the length is less, because in over square engine, the distance traveled by the piston will be small. And other efficiencies, how it's defined is, you have an indicated thermal efficiency or a brake thermal efficiency. Indicated power is the maximum power which is generated, and brake power is the indicated power minus friction power, the power lost due to friction. So that then you will get the brake power, and Q is the total amount of energy you supply. So there is a term called combustion efficiency, which is divided by Q, the energy provided, divided by the maximum calorific value of the fuel, which energy which the fuel can provide. If you assume that combustion efficiency is 1, then the indicated thermal efficiency will become IP by m dot C. And there is a mechanical efficiency term defined, which gives you brake power by indicated power, or you can also calculate by brake mean effective pressure or indicated mean effective pressure. So the mean effective pressure is the you can say, if the piston moves at the constant pressure for the displacement volume, what is the amount of work which you will get. So that will give you the mean effective pressure. So if you want to get an indicated power, so that will define indicated mean effective pressure. For brake power, it will define brake mean effective pressure. So it's just that work is generally work in case of piston is generally defined as P delta V, or P into this displacement volume. So that P you generalize it, average it, so that is the mean effective pressure. So that you can find out the brake power or the indicated power directly. And then you have a volumetric efficiency, which is defined as the mass of air which is coming in, and the mass of air which divided by the mass in the swept volume. So those are the major terminologies which is used in engineering. Now we'll go ahead and see how the 4-stroke IC engine works. So as you can see, 4-stroke, you have the piston at the topmost position. So when this piston moves down, it will create a vacuum, and the inlet valve opens. Because it's expanding, the pressure will go down inside. So the inlet valve will open, and the air-fuel mixture will come in. So once the piston reaches the bottommost dead center, it will start compressing again the air plus fuel mixture which is inside. So it will start compressing it. So once it reaches the top dead center, based on the valve timing, based on where this spark plug is initiated, so the combustion will take place. So after when the combustion takes place, the fuel will be combusted, and then it will start expanding. It will push the piston down. So that is the power stroke, which will generate power. And next, once the piston has moved to the bottommost position, the piston is again moved up, compressed, and the valve is open, so that the gases exhaust gases which are present can be removed out. So this is general idea of how the 4-stroke engine works. So this is an example of the SI engine, spark ignition engine. So in case of an compression ignition engine, what will happen is, instead of spark plug, you will have an fuel injector. So when the piston in the second position, when it reaches the topmost position, when it has compressed the air, fuel is injected. So because of compression, the air inside would have been at higher temperature. This temperature is equal to or greater than the fuel's combustion temperature. So that because of that, the fuel, when it is injected, it will start combustion. It will it will start reacting with the air. It will combust and it will form exhaust gases, and which is removed again. So that is the difference in the compression ignition engine and the spark ignition engine. But the idea is same. It's called 4-stroke because there are 4 strokes happening for a cycle to complete. So when it's going down, going up, there's a power stroke for expanding, and then for exhausting, ignition is moving up. So 4 strokes is happening. So that's why 4-stroke engine. So you need true revolution for a single cycle to complete, out of which there is only one power stroke. So that is 4-stroke IC engine. And if you see for a 2-stroke internal combustion engine, what will happen is this is at the topmost position. So the spark is ignited, it has been compressed, the fuel has been compressed, and the fuel air mixture is present. So spark is ignited, so it will combust and it will move the piston down. So the piston will, that's the power stroke, it will come down. When it moves down, what will happen is initially the pressure will be higher, it will be moving towards exhaust. When once the inlet port is open, so the fuel air mixture, initially when the combustion is happening at the top, what will happen is inlet port, this has expanded. You can see, can think of it as a 2 cylinders. One is at the top, one is at the bottom. Once the compression is happening at the top, there is expansion at the bottom. The crankcase also is taking into operation. So what happens is the inlet port is open, so inlet there will be fuel air mixture coming in, which will be there at the bottom of the crankcase. So once the piston is moved down because of the combustion, it will compress the fluid down. So that will push the fuel air mixture once the inlet port is open. So once the inlet port is open, the fuel air mixture which is there in the crankcase will come up. It will displace the exhaust gases which is present in the cylinder. So this process is called scavenging. And once this is done, the piston will retrace and it will start compressing the fuel air mixture which is present in the cylinder. And during compression, the inlet port will open and it will take in fuel air mixture from to the crankcase. So that goes through cycle. So fuel air while exhaust gas are removed and piston is compressing, there is a inlet fuel air mixture coming into the crankcase. Then inlet fuel air mixture which is present in this combustion chamber, which has been compressed, is ignited, and then piston comes down. It will reduce the volume in the crankcase. So there will be increase in pressure. Only inlet port is open, this mixture will enter the combustion chamber and it will displace exhaust gas, and that is scavenging. So and then the piston moves up, start compressing, then the process repeats. So that is a 2-stroke IC engine. You see there will be 2 strokes happening for a cycle to complete. So hence 2-stroke engine, and there is a cycle completes in 1 revolution. So 2-stroke, 1 revolution, and 1 power stroke in each of the revolution. And 4-stroke engine, 4 strokes in 2 revolution and 1 power stroke. In 2 strokes, 2 strokes, 1 revolution and 1 power stroke. So that is the difference between and the pistons are arranged and such that it moves the inlet air which is coming in, and based on the inlet air and the exhaust port which is present, the type of scavenging can be of different types. So So the inlet port can be bottom at the bottom, and exhaust port can be at the top. So it will go through a loop. So that can also be placed. So different arrangements of inlet and exhaust ports can be possible. Now we'll see what are the comparison of the 4-stroke and a 2-stroke cycle engine. If you see completion of cycle, how the cycle is completed. The cycle is completed in 4 strokes, as I told you, and in 2 revolution of the crankshaft. So there is 1 power stroke in every 2 revolution of the crankshaft. So that is a 4-stroke cycle. If you see in a 2-stroke cycle, the cycle is completed in 2 strokes of the piston, in 1 revolution of the crankshaft, and 1 power stroke for each crankshaft revolution. If you see a flywheel, as I told you previously, the purpose of a flywheel is to store energy and provide a smooth operation. So this case flywheel, because the above turning movement is not so uniform, hence heavier flywheel is needed, because in 2 revolutions you are generating only 1 power stroke, so that's why you need a heavier flywheel. But in case of a 2-stroke, more uniform turning movement, and hence lighter flywheel is needed, because you are generating every revolution there is a power stroke, so you need a very lighter flywheel. And if you see power produced for the same size of engine, because of 1 power stroke for 2 revolution, power produced for same size of engine is small, or for the same power the engine is heavy and bulky. But so opposite will be true for the 2-stroke. So engine will be small and the power stroke will be more. So theoretically twice, actually about 1.3 times. That is the power generated for the same size compared to the 4-stroke cycle engine. If you see cooling and lubrication requirement, so it will require less power, less cooling and lubrication, but it will require more cooling and lubrication. And valve mechanism, it has no valves in 2-stroke. It has only ports for inlet and outlet, and exhaust may have valves. So initial cost, if you see, because the engine is heavy, so manufacturing cost and material cost will be more. So, and valve mechanism is complex, so 4-stroke engine will be costlier compared to 2-stroke engine. And if you see volumetric efficiency in case of 4-stroke engine will be more, because the piston is compressing and it's removing all the exhaust gases, but all the exhaust gases will not be removed. It's not possible to remove, so volumetric efficiency will be less compared due to lesser. So, and thermal and part load efficiencies. So thermal efficiency will be higher and part load efficiency will be better than 2-stroke engines, and it will be poorer in case of 2-stroke engines. So that is in comparison. So we'll proceed with some MCQs. So the process of inducting pressurized air in the engine cylinder is called as, so the process of inducting pressurized air, from the normal air you are getting a pressurized air, relatively pressurized air. So this process is called as A, turbulence, B, pre-ignition, C, supercharging, D, both A and B. So see, your inlet air is pressurized, so that can happen in 2 processes. One is turbocharging or a supercharging. So in this case, one C is supercharging. Supercharging is you put up you are basically compressing the air in the inlet. So it can be driven by the crankshaft, or in case of supercharging, and it can be driven by the exhaust gas in case of this is in case of turbocharging. So the exhaust gas is driving and it can compress the air, inlet air. So that is one case, and the other case you are taking power from the crankshaft. So the one will consume power from the crankshaft, one is you are using the exhaust air which is going out. So that will give a better efficiency compared to supercharging. So, but both processes will give you pressurized air. So the process of injecting pressurized air in the engine cylinder is called as supercharging. The second question is, the mean effective pressure measured from the engine indicator diagram shows the mean effective pressure measured from as I told you what is mean effective pressure. So indicator diagram is the PV diagram which you plot to calculate the process. So the cycle is plotted in the PV diagram. It's called an engine indicator diagram. So this mean effective pressure which is calculated from this diagram will give you what maximum pressure, minimum pressure, instantaneous pressure, or average pressure. So you know the word itself, the question itself says what is it, mean effective, mean, so it will be average, so it will be answer D, average pressure. In the indicator diagram you can get maximum pressure, minimum pressure, or at that point corresponding volume what you can be the pressure, that is an instantaneous pressure. You can get all this thing, but mean effective pressure is the average pressure in which the cylinder is operating, so that you can get the power. So P into delta V, as I told you. V is displacement volume, and what pressure if the piston is moving on an average, so that you will get that power. So that is mean effective pressure. So that is generally the average pressure. So the next question is, the percentage of energy lost through exhaust in case of a spark ignition engine is higher than that of compression ignition engine. So in both the cases, you are after combustion happens and after the power stroke, the piston compresses and the gases, the remaining gases present after combustion. So the products of combustion which are there, and if the combustion is not fully done, so there will be some initial fuel will also be present. So these are the exhaust which is removed. So this exhaust has higher energy in case of SI engine or a CI engine. That's the question. So percentage of energy lost. So the percentage of energy lost in case of SI engine is more compared to CI engine. So the statement is true. Why is it? Because the SI engine operates at a higher RPM. So higher RPM means at each there is a multiple, the piston is moving relatively more compared to the CI compression ignition engine, which is operating at lower RPMs. So hence more amount of mass is being pushed out, and also it is at combustion temperature will be at higher temperature compared to the compression ignition engine. So because of higher temperature means more energy. So you are rejecting or putting out more energy exhaust gas in case of an spark ignition engine compared to a compression ignition engine. So hence the statement is true. And moving on, the next question is, an engine indicator diagram is used to determine dash. So as I told you previously, engine indicator diagram is a cycle in the PV diagram. So that is used to determine what? A, speed, B, mean effective pressure, C, indicated horsepower or indicated power, D, both mean effective pressure and indicated horsepower. So using this indicator diagram, what can you calculate? That's the question. So as I previously saw, you can calculate the indicated power, the total power the cycle can generate with area under the cycle. You can calculate the indicated power. Then mean effective pressure is just the indicated power divided by the displacement volume. So the power, the mean or average pressure in which that is operating. So that also can be calculated if you calculate the power. So you can calculate both mean effective pressure and indicated horsepower. Speed you cannot calculate because in the case of engine how it operates, the frequency. So the indicator diagram only shows you the cycle. It cannot show you the number of cycles happening per minute. So A is not true. So B and C both can be calculated. So the answer is option D, both mean effective pressure and indicated horsepower. So moving on to the next question, we have if the intake air temperature is decreased, then the efficiency of engine will dash. So engine is operating at some condition, you are getting inlet fuel and air mixture coming in, and it's combusting and it's exhausting. That's the process. So the inlet air which is coming in, either in case of compression ignition or a spark ignition, the air which you are putting in, if you reduce the temperature, so what can happen? If you reduce the temperature, if you see using ideal gas law, you assume that air is an ideal gas, so that will be equals to, or you can write P equal to rho RT. P is pressure equals to rho density into R by T. So density and temperature are inversely proportional. So if the temperature is reduced, density will increase for the same pressure. So you are holding pressure constant. So if your temperature is reduced, so the density will increase. So you can say in terms of more volumetric efficiency, it's more mass coming in. So that is one case, and the temperature also low, it can expand to a higher temperature. So can expand more. So this will hence this will increase more. It will generate more power. So as this generates more power, your engine efficiency is also better. So hence this will create an increase in efficiency of the engine. So when intake air comes in, it's the density of the air coming in has increased slightly, and it can also expand more. So it will increase. The next question given is, the firing order in an IC engine depends upon A. cylinder arrangement, B. crankshaft design, C. number of cylinder, D. all of this. So the firing order in an IC engine depends upon. So the firing order, what does it mean is, in you have multiple cylinders in an engine, in what order the cylinder should be fired. For example, you have 4 cylinders, the firing order can be 1 4 3 2, or 1 2 3 4, or all 4 together, or 1 4 together, and the combination, how the spark plug should be ignited to the combustion. So that's the question what is been asked. So this firing order, how is it determined? So A, cylinder arrangement. So yes, cylinder arrangement also matters in case of firing order. If a V shape or and all cylinders are inlined, so it will have a different firing orders, because each of the cylinder will generate a power stroke. So that power stroke is being transmitted to the crankshaft, and for a smooth operation also the crankshaft to not fail. So that also to be taken into account. So that will determine the firing order for the cylinder arrangement. Will determine what all cylinders are generating power stroke together or at a time. So that will determine the firing order. And next, also for smooth operation, the firing orders are placed such that the crankshaft is getting rotated uniformly, or there is a smooth power generated. So cylinder arrangement matters in firing order, and the crankshaft design is also depend upon firing order. And as I told you, number of cylinders will also matter, because it depend how the cylinders are generating power strokes, and how many cylinders are there. So firing order will depend upon that also. So in this case, all of these will determine will depend on the firing order. So answer is D. And the next question is, mechanical efficiency increases with increase in dash. So mechanical efficiency, as so we saw in the terminology or the nomenclature part of the engine, we saw efficiencies as well. So mechanical efficiency is defined as brake power divided by indicated power. Indicated power is the maximum power which the cycle generates. So brake power divided by the indicated power. So brake power will reduce if you have more friction. So friction power, if it's increasing, brake power will reduce. So if the friction power is reducing, so brake power will go up. So brake power by indicated power will be constant, so brake power will increase. So for the mechanical efficiency to increase, your brake power should increase. So hence mechanical efficiency increases with increase in brake power. Because indicator power is nothing but brake power plus friction power. So for an indicator power, if brake power increases, mechanical efficiency increases. The number of working strokes per minute for a two-stroke engine is dash the speed of the engine in RPM. So engine rotations per minute is equals to number of working strokes per minute for a two-stroke engine. As I told you previously, we saw 4-stroke engine has 1 power stroke in 2 revolutions of the crankshaft, and it has 2 strokes. 4 strokes for 4-stroke engine, 1 power stroke in 4 strokes of the engine in 2 revolution of the crankshaft. And in case of 2-stroke engine, the question which is asking, you have 1 power stroke for 2 strokes of the cycle and 1 revolution per 1 revolution of the engine. So in this case, the number of working stroke is the power stroke. So the power stroke is equal to the revolution. So you have 1 power stroke for 1 revolution of crankshaft. The speed of engine is same. So number of working strokes per minute will be equal to the speed of the engine. So hence it will be equal to. Next is given is if W is the brake load. So this is a question of a dynamometer to evaluate the brake power. So this is a case of a spring rope dynamometer. Rope drum dynamometer. So you have a brake, a load, and you have a spring in which a rope is attached, and this rope goes over a drum which is connected to the engine, and this rope goes around the drum, and a load is kept at the bottom. So this load weight is W, or the force is generating is W, and the spring force is given, spring balancer reading force is given as S, and the rotation at which the engine is rotating is N, and L is the length of the arm, D is the brake drum diameter, and D is the rope diameter. So brake drum diameter and rope which is going around. So the relation of brake power of the engine can be expressed as the answer is option C. So as I told you, we have an engine shaft which is put into a drum, so which is of brake drum which is of diameter D, capital D, and then you have rope diameter D, small d, and this is attached to a spring and the weight W. So if you see, the tension in the spring is W minus S, because this load is acting and it's giving force W, and the spring is generating S. So the difference in force is what is the tension in the string. So that is W minus S. That will create a torque. So the radius will be capital D plus small d by 2. So that is the radius, effective radius. So torque will be W minus S into D plus capital D plus small d by 2. And if you see for power, it will be 2 pi N into torque by 60 if the revolution is in to convert it into RPM or per second. divide by 60. From n is in rpm, speed is in rpm, so divide by 60 to convert into seconds. And 2 in the diameter gets cancelled out, so you get w minus s into capital D plus small d by 2 into 2 pi n divided by 60. So 2 cancels out, you will get w minus s into pi into d plus d into n divided by 60. So the answer is option C. So the next question is, in general, the thermal efficiency of a two-stroke engine has a lesser value than a four-stroke engine. So in general, the thermal efficiency of a two-stroke engine has a lesser value than the four-stroke engine. So this is true, as we already saw. In two-stroke engine, the fuel will not be fully combustible, and you will have some exhaust gas also present inside the engine. So it will be, answer is option A, true. So let's see some numericals. We have a 4-cylinder 2-stroke cycle diesel engine, so combustion engine, and it has 4 cylinders with 10.9 centimeter bore diameter and 12.6 centimeter stroke length. So you have 4-cylinder diesel engine, 2-stroke cycle, and the diameter of the cylinder is given 10.9 centimeter and the stroke length is 12.6 centimeter. This cylinder is producing a brake power of 88 kilowatt, and this is running at 2000 rpm, and they have also given that compression ratio is 18:1. So for this case, we have been asked to calculate engine displacement, brake mean effective pressure in kilopascal, torque and clearance volume of one cylinder. We have 4 cylinders, clearance volume in one cylinder, that's what we have been asked to calculate. So we will start with engine displacement. Engine displacement is the displacement volume. So engine displacement volume is nothing but the volume of this cylinder in the stroke length. So pi by 4 into bore diameter square into stroke length. So that will give you engine displacement. So we'll see how to solve it. So engine displacement is pi by 4 into b square is the bore dia into s stroke length. So this is the displacement volume, and NC is for the number of 4 cylinders. So the total displacement volume we will get. So 4 into pi by 4 into 10 power 0.9 square. 10.9 is the bore and 12.6 is the stroke length. So substituting that, we will get 4703 centimeter cube or 4.703 liter. So 4.7 liter engine. So that's the capacity of engine. So engine displacement capacity, and then the next question was to find out the brake mean effective pressure in kilopascal. So brake mean effective pressure is we know the brake power. So brake power divided by the displacement volume. So displacement volume is this is per second for in each stroke length. This is the displacement volume, but this is happening. This engine the engine is running at 2000 rpm. So taking that into account, and 88 in kilowatt, 88 into 1000 to convert it to watt, divide by displacement volume 4.703 into engine is running at 2000 rpm, so 2000 divided by 60 to convert it into seconds. So solving this will give you 561 kilopascal. So that is the brake mean effective pressure. Then the next question was to find out the torque generated by the engine. So torque generated is brake power is, we can the other form of writing brake power is 2 pi into nt, that is t into omega. 2 pi nt. So we know n, we know brake power, so by substituting we can calculate. The other way is using the brake mean effective pressure, which we have calculated. So that into displacement volume divided by 2 pi, that can also give you torque. So we'll use the first one. So brake power is 88. We are converting it to watt. Divide by 2 pi into n. We know 2000 by 600. So we'll get 42 420. So torque generated in this engine is 420 Newton meter. So the next question was find out the clearance volume of one cylinder. As you can see, we know the compression ratio, and compression ratio is nothing but the total volume by clearance volume, and you can also write total volume as clearance volume plus the displacement volume. So here we know displacement volume we have calculated for 4 engines, 4 cylinders. Now we need displacement volume in a single cylinder. So we divide the displacement volume by 4. So we get 1176 centimeter cube. This is the displacement volume or swept volume in a single cylinder. And we know the compression ratio, which is 18. So we know displacement volume, we know compression, we can calculate the clearance value in this case. So this is VC will come out to be 69.2 centimeter cube. This is RC is VD plus VC by VC, not VD, it's by VC. So we can calculate VC as 69.2 centimeter cube. So the next question is, we have a 4-cylinder 2.4 liter engine which is operating on a 4-stroke cycle at 3200 RPM. So 4-cylinder, same 4-cylinder, but this is operating at 4-stroke, and the engine capacity is 2.4 liters, and this is operating at 3200 RPM. Again, they have given the compression ratio is 9.4. The connecting rod length is 18 centimeter, and the bore and stroke are related as S equals to 1.06 B. So calculate clearance volume of one cylinder, bore and stroke, and average piston speed. So that's what we have been asked to calculate. So first is the clearance volume of one cylinder. So we know the displacement volume of engine or capacity of engine is 2.4 liters for 4 cylinders. So for each cylinder will be 2.4 by 4, which will give you 0.6 liter or 600 centimeter cube. So that is the displacement volume of a single cylinder. Now we know the compression ratio is 9.4. Similarly, compression ratio you can calculate VC is 71.43 centimeter cube. Again, this is VD plus VC divided by VC. It's not divided by VD, it's divided by VC. So it will come out to be 1 plus VD by VC. So the clearance volume is 71.43. Then we need to calculate bore and stroke. So we know the displacement volume, and the displacement volume is expressed in terms of bore and stroke. It's for single cylinder it will be pi by 4 into B square into S, bore square into S. So this is the volume of the cylinder. So VD into VD we know for single cylinder is 600 centimeter cube. We know pi by 4. We know B square and S is related. B is related as to S as 1.06 B. So we substitute the stroke length. So we can find out it will become 600 equals to pi by 4 into 1.06 B cube. So we can find out B from there. So the bore is 8.97 centimeter. On substituting in the stroke length relation, we will get S is 1.06 into 8.97, which is 9.5 centimeter. So this is under squaring it. And if you see, next question is to find out the average piston speed. So the average piston speed is given by 2 into S into N. So it's a 2 strokes per revolution. So 2 into 0.095 the stroke length into N is the number of rotations. So 2 into 0.095 into 3200 by 60. So you'll get the piston speed as 10.13 meter per second. So we calculated everything. The average piston speed is 2 into S into N. Moving on, the next question is, we have a high performance 4-stroke spark ignition engine which has a swept volume of 875 centimeter cube and has a compression ratio of 10:1. So we know swept volume 875 centimeter cube. This is for a single cylinder, and compression ratio is also known 10. They are given that indicated efficiency is 55% of the corresponding ideal air standard Otto cycle. So they say indicated efficiency is 55% of the Otto cycle efficiency. So that's one relation which we know. And they say at 8000 rpm the mechanical efficiency is 85% and the volumetric efficiency is 90%. The air fuel ratio, that is by mass, is 13:1 and the calorific value of the fuel is 44 megajoule per kg. So a lot of detail has been given. It's been operating at 4-stroke. The swept volume is 875 centimeter cube. Compression ratio is 10. They say indicated efficiency is 55% of the Otto cycle efficiency, and the engine is operating at 8000 rpm. Mechanical efficiency is given 85%. Volumetric efficiency is given as 90%. Air fuel ratio in terms of mass is given as 13:1. Calorific value is 44 megajoule per kg. So these are the details we know. So the air is coming in at 20 degrees Celsius and 1 bar. Calculate specific fuel consumption if the Otto cycle efficiency is 60.2%. So we have given Otto cycle efficiency is 60.2%. You need to calculate the specific fuel consumption. The second one is the air mass flow rate, power output, and brake mean effective pressure. So we need to calculate specific fuel consumption and air mass flow rate for and then power output and brake mean effective pressure. So 4 things we need to find. So we'll see how to solve. So for specific fuel consumption is defined as m dot by work. So that is the amount of mass it's taken in, or the fuel taken in by the power generated. So that is how the specific fuel consumption is defined. And then if you write in terms of overall efficiency, so power is thermal efficiency. Brake power can be written in terms of thermal efficiency into, or overall efficiency into the combustion energy which is provided. So m dot f into c. So m dot f will cancel out. So we will get 1 by calorific value into overall efficiency, or thermal efficiency. So we know that overall efficiency in the question is given is the mechanical efficiency into indicated efficiency. Indicated efficiency is the brake power, indicated power divided by the energy provided by the fuel, m dot f into cv. That is indicated efficiency. And mechanical efficiency is brake power by indicated power. So we can find out overall efficiency is brake power by m dot into cv. So that gives you relation. Because we don't know directly the overall efficiency or the thermal efficiency, we have been given mechanical efficiency and indicated efficiency, but they say indicated efficiency is 55% of the Otto efficiency. So Otto efficiency is, the question, 60.2%. So on substituting this, we can find out indicated efficiency. We substitute indicated efficiency and we know mechanical efficiency is 85%, 0.85. So overall it will come out to be 0.281, so 28.1%. So overall efficiency is 28.1%, or brake thermal efficiency is 28.1%. Substituting that, and we know the calorific value of the fuel, which is 44 megajoule per kg. So substituting that, we'll get specific fuel consumption is 0.0809 kg per megajoule. So this is the specific fuel consumption, brake specific fuel consumption. So I'll say again, specific fuel consumption is m dot f, mass of fuel, divided by brake power. This is brake specific fuel consumption. So m dot f divided by brake power. Brake power can be calculated from the overall efficiency or the brake thermal efficiency as brake thermal efficiency into m dot f into CV. So m dot f cancels. So brake specific fuel consumption will give you 1 by CV into thermal efficiency. And this is defined as mechanical efficiency into indicator thermal efficiency, and based on the relations given and the values given, we can find out the overall efficiency. We substitute that, we know calorific value, we substitute that, we will get specific consumption as 0.0809 kg per megajoule. The next question was to find out the mass flow rate of air. In the question we have been given the stoichiometric ratio or air fuel ratio. Sorry, it's not a, we don't know whether it's stoichiometric, but the air fuel ratio is 13:1. So for air, assuming it to be an ideal gas, we write PVA equals m dot A into RAT. So gas constant for air is 287 joule per kg Kelvin, and V dot A is V swept volume into volumetric efficiency into n star. N star is the rotations happening. So for divided by 2 because of 4-stroke engine, because there is only one inlet coming in for 2 strokes, so by 2. So V dot A is, we know swept volume, we know volumetric efficiency, and we know in number of rotation of this engine. So we substitute that in terms of VA, so and divide by RAT. So using this we can calculate, we know pressure, for 1 bar, and 875 is the displacement volume given, and 1070 is centimeter cube, so converting to meter cube, and volumetric efficiency is 90%, 0.9. So and the engine speed is 8000, so 8000 divided by 60, and for in case because of 4-stroke divide by 2, so it will become 120, 8000 divided by 120, and 287, and temperature is 293, because the question is given air inductor is 20 degrees Celsius and 1 bar, so 273 plus 20, 293. So solving this, we will get mass of air coming in is at 0.0624 kg per second. So we have calculated the mass flow rate. The next question is to find out the power output. So we have calculated m dot A, so we can calculate air fuel ratio, we know, so we can calculate the mass of fuel. So mass of fuel by mass of A is mass of air by mass of fuel is air fuel ratio. So m dot A divided by 13, so we can calculate mass of fuel, and brake power is nothing but we have already calculated specific fuel consumption, which is m dot f divided by brake power. So brake power is just m dot f by specific fuel consumption. So we have already calculated that, and we know mass of fuel. So on substituting, we will get 59.3 kilowatt. So calculated brake power output. The next question is brake mean effective pressure. So for brake mean effective pressure is nothing but brake power divided by swept volume, and brake power is we have calculated 59.3 kilowatt, and respect to volume is 875, or displacement volume is 875 into 10 power minus 6 into n is 8000 speed. The engine is running at 8000 rpm, so divide by 60, and because it generates only one power stroke for 4, this is a 4 stroke engine, so divide by 2. So doing so we will get 10.2 bar. So the brake mean effective pressure is 10.2 bar. So moving on, we have a 6-cylinder 4-stroke automobile engine is being designed to produce 75 kilowatt at 2000 rpm. So we have a 6-cylinder 4-stroke engine which is designed for running at 75 kilowatt and 2000 rpm with brake specific fuel consumption of 300 grams per kilowatt hour. Brake specific fuel consumption is given. Brake mean effective pressure is 12 bar, so that is also given. So the engine is to have equal bore and stroke and fueled with gasoline with a heat of combustion of 44 megajoule, 44.51 megajoule. What should be the design displacement volume and bore? So that is the first question. What is the mean piston speed at the design point? Mean piston speed is asked. And what is the fuel consumption per cycle per cylinder? Next question is, what is the brake thermal efficiency? So four been asked. So it's a 6-cylinder, we know brake power, rpm we know, brake specific fuel consumption we know calorific value of the fuel, brake mean effective pressure. So let's see how to solve. First is engine displacement, volume and bore. So engine displacement is nothing but we know brake mean effective pressure. Brake mean effective pressure is defined as WB, or brake power divided by displacement volume into the revolution. So n is the rotation rpm, engine speed, divided by 2 because of 4-stroke engine, and it's generating only one power stroke per 2 revolutions, so you divide by 2. So and we know brake power 75 kilowatt, divide by brake mean effective pressure is 12 bar, so 1200 kilopascal into n is 2000. Here if you write it in pascal, you have to write the brake power is also in watts. As I have written this into a kilopascal, so I am keeping this in kilowatts. So 75 divided by 1200 into speed is 2000 divided by 2 divided by 60 to convert it into seconds. So this will give me displacement volume as 3.75 into 10 power minus 3 meter cube, or 3.75 liter. So we have calculated the displacement volume. And the bore volume is, we know displacement volume, so we can calculate the bore diameter. And the question says that it is a bore and stroke are equal, so that's a square engine, so B equals to S. So on substituting that, displacement volume is pi by 4 into B cube into number of cylinders, so that's the expression. So we can find out the bore diameter from here and see the number of cylinder, which is 6-cylinder. So displacement volume per cylinder is 3.75 divided by 6, and converting it to meter cube into 4 by pi raised to power 1 by 3, so it will give you 92.7 mm. So the bore diameter is 92.7 mm. The next question was to find out mean piston speed. As I have already seen, mean piston speed is 2 into stroke into the speed. So 2 into 9.27 into 10 power minus 2 is stroke length, because bore diameter is equal to stroke length, into 2000 divided by 60. So this will give you 6.18 meter per second. So this is the mean piston speed. So the next question is the cycle average fuel consumption rate per cylinder. average fuel consumption rate. So, or m dot f per cylinder, that's what it's been asked. So we know brake specific fuel consumption. So brake specific fuel consumption is m dot f divided by wb, brake power. So brake power per cylinder is wb divided by number of cylinders. So 300 divided by into 75 divided by 6, and so this will give you me in 62.5 grams per minute. So this is this fuel consumption per cylinder per minute. So 62.5 grams per minute. Now I want how much per second, so or total amount of fuel which is consumed. So 62.5 divided by 2000 divided by 2, because this is a 4-stroke engine, so n divided by 2. Thing to remember is n will not be n by 2 only in case of mean piston speed, but others you have to use n by 2 for a 4-stroke engine. So m dot f will become 6.25 into 10 power minus 2 grams. This is 10 power minus 2. So that is the average fuel consumption rate in a cylinder. So the next question is, last was to find out the brake thermal efficiency. So the brake thermal efficiency is defined as brake power divided by so brake power divided by the Q. So brake power is can find it in terms of brake specific fuel consumption. So m dot f by brake power is brake specific fuel consumption. So m dot f by brake specific fuel consumption, you can substitute brake power here, so it will become 1 by brake specific fuel consumption into m dot f into calorific value. M dot f cancels, so it will come out to be 1 divided by brake specific fuel consumption into calorific value of the fuel. So on substituting that, we will get 3600 yeah. So brake specific fuel consumption is 300 grams per kilowatt hour. So so it will become 0.3 watt divided by 3600 in terms of watt per second. So using that, divide by calorific value is given as 44,510. Substituting that, we will get 0.27 as the brake thermal efficiency. So the next question is, we have a 4-stroke 2.5 liter direct injection automobile engine. So it's again 4-stroke engine with a 2.5 liter capacity of the engine. So we know the displacement volume of the engine. It's tested on a dynamometer at a speed of 2500 rpm. So speed of the engine is also known. So this is producing a torque of 150 Newton meter, and its volumetric efficiency is measured to be 0.85. So volumetric efficiency is known, torque is known, speed is known, capacity of engine is known. So what is the brake power, the mass airflow rate through the engine? So inlet pressure and temperature are 75 kilopascal and 40 degrees Celsius. Okay, so what we need to find is the brake power and mass flow rate. We have seen a similar problem, so the same approach. Brake power is, we know torque, so 2 pi nt. So 2 pi in the torque is 150 Newton per meter, and we know the speed of how it's rotating, 2500 divided by 60. So that will give us 39.3 kilowatt. Next question is to find out the mass flow airflow rate. So the density is P by RT. So inlet density. So we will calculate inlet density as, we know 75 kilopascal pressure, R is 287, and temperature 273 plus 40, so 313. Substituting that, we'll get density of air is 0.835 kg per meter cube. So a volumetric efficiency is defined as m dot A divided by rho into displacement volume into number of rotations. So m dot A is half into volumetric efficiency is 0.85. So rho is, we have calculated 0.835, and displacement volume is 2.5 liter into 10 power minus 3 into 2500 divided by 60. So that will give us 3.70 into 10 power minus 2 kg per second. Actually this will be divided by 2, so this will become 3.1.1.85 in 10 power minus 2 kg per second. So that is the mass flow rate, and change this. Okay. So the next question is, you have a Rolls-Royce CV12 turbocharged 4-stroke direct injection diesel engine. So just continue. It's a T12 to 12 engine. So it has a displacement of 26.1 liter. The engine has a maximum output of 900 kilowatt. So we know the brake power, and it says that the speed of the engine is 2300 rpm. Next is, and it's derated to 397.5 kilowatt at 1800 rpm for industrial use. Engine was built for 900 kilowatt and 2300 rpm, but for industrial use it's operated at 397.5 kilowatt at 1800 rpm. So what is the brake mean effective pressure for each of these cases? So that is the first question. The next question is, the high performance version of the C12 has a brake specific fuel consumption of 0.063 kg per megajoule and at maximum power, and a minimum specific brake specific fuel consumption of 0.057 kilogram per megajoule. So calculate the arbitrary overall efficiency for both conditions, or overall efficiency for both the condition and the fuel flow rate at maximum power. Values given. So we'll see how to solve this. The first question is to calculate the brake mean effective pressure. So brake power is brake mean effective pressure into displacement volume into N. So N is in revolution per second divided by 2 because 4-stroke engine. So rearranging this will give me brake power divided by displacement volume into the N. So substituting this brake power for first case 900 kilowatt and 2300 rpm. So 900 into 10 power 3 to convert it into watts divided by 26.1 in 10 power minus 3 because 26.1 liter engine. So displacement volume is 26.1 1 liter. So converting into meter cube into 10 power minus 3 into speed is 2300 divided by 60 divided by 2 because of 4-stroke engine. So this will give me 18 into 10 power 5 Newton per meter square. So this will give me 18 bar. So for the industrial engine case, the brake power is 397.5 and the speed is 1800. So substituting that, 397.5 into 10 power 3 divided by 26.1 for displacement volume into 10 power minus 3 into 1800 divided by 60 divided by 2. So this will give me 10.15 into 10 power 5 Newton per meter square. So 18 bar and 10.15 bar. So that is the brake mean effective pressure. So we have solved the first question. So moving on to the next question. we know the brake specific fuel consumption is 1 by overall efficiency into calorific value. So at maximum power, we know at maximum power the brake specific fuel consumption is 0.063 and calorific value is 42. So at maximum power, the overall efficiency will be 0.063 into 42. So it will give me 37.8%. And the other condition was minimum brake specific fuel consumption, or minimum means maximum economy. So at maximum economy or minimum brake specific fuel consumption, so the overall efficiency will be 1 by brake specific consumption into calorific value. Brake specific fuel consumption is 0.057. Substituting that, we will get 41.8%. You can see there's a 4% increase in overall efficiency. So finally, the question is also asked to calculate the fuel flow rate at maximum power. At maximum power is a 900 kilowatt, and specific fuel consumption is 0.063. So brake specific fuel consumption is m dot f divided by brake power. So m dot f will be brake specific fuel consumption into brake power, which will give me brake power is 900 into 10 power 3 watts. Brake specific fuel consumption is 0.063 into 10 power minus 6, because kg per megajoule. So we are converting it to joule. This will give me 0.0567 kg per second. So that is the fuel consumption per fuel consumption with maximum power. So calculate everything. The only thing to remember is to divide by 2 in case of a 4-stroke engine, but 2-stroke engine we don't need to worry about that, so it will not come, so n will be same. And here the overall efficiency, it's easier, we need to just substitute the calorific value and the brake specific fuel consumption, you can get the efficiency. Okay, that's it. Thank you.